Hey everyone, and welcome back for another deep dive with me.
Boy.
You ready to get a little nerdy today?
Always.
Okay, excellent. I'm so pumped for this one. We're talking about mental heterogeneity today.
Ooh. Sounds a bit intimidating.
I know, right? It's gonna be so cool.
Oh, it's fascinating stuff.
Okay, so before we get too deep into this, pun intended,
Yep.
can you give us a quick rundown of what mental heterogeneity actually is?
Yeah, so basically it means that the Earth's mantle, that giant layer of rock beneath the crust,
Right.
it isn't just one big uniform blob.
Okay.
It's got these distinct regions with different chemical compositions.
So it's not just like one kind of rock all the way down.
No, not at all.
Ooh, okay. I like where this is going.
Yeah, we've got some fascinating research to dig into today.
Okay.
It's a recent paper from Nature Geoscience.
Okay.
And it's called Large-Scale Mantle Heterogeneity as a Legacy of Plate Tectonic Supercycles.
Ooh, supercycles. This already sounds epic. I hear this research is shaking things up a bit because for a long time, scientists thought that this heterogeneity was mostly a north-south thing, right?
That's right.
Like the DUPL anomaly.
Yeah, the DOPL anomaly.
But this paper's like, no, no, no.
It challenges that idea.
It really does.
Yeah, it turns out that it's not so much about north versus south as it is about east versus west. So there's a distinct chemical difference
Interesting.
between the mantle underneath Africa and the mantle underneath the Pacific Ocean.
So like the Earth has its own version of East Coast versus West Coast,
Yeah, exactly.
but on a planetary scale.
That's right. And what's really cool is how this connects to plate tectonics and the supercontinent cycle.
Okay, so we're talking about like Pangaea,
Yeah, you got it, Pangaea.
that giant supercontinent.
Exactly.
Okay.
And this research suggests that the way that the continents arranged and the oceans closed during Pangaea's formation actually concentrated more continental material into the African mantle domain.
Oh.
And that's what makes it chemically distinct from the Pacific side.
So it's like Pangaea contaminated the African mantle domain.
Yeah, you could put it that way.
Interesting.
Yeah, and it added in all these bits and pieces from the Earth's crust.
And like, how do they figure that out?
Yeah.
Like, I mean, we can't just like dig down there and see.
No, it's not like we can just like take a scoop.
Right.
Right.
Like, so how are they figuring this out?
So they actually analyze different types of volcanic rocks,
Yep.
like mid-ocean ridge basalts, or MRRBs.
MRBs.
Yeah, which form where tectonic plates pull apart.
Okay.
They also look at ocean island basalts, or OIBs.
OIBs.
Yeah, and oceanic plateaus, which are also known as OLAPs.
OAPs.
Yeah, and those come from those deeper mantle plumes.
Okay, so they're looking at different flavors of rock to understand the mantle's history.
Exactly.
And speaking of flavors,
Yeah,
does that mean that there are different types of MORBs?
you bet.
Okay.
Scientists categorize them as NMRB, DMRB, and EMRB, each with a slightly different chemical composition.
Okay, so we've got normal MORB, depleted MORB, and enriched MORB.
Exactly.
Okay.
Hey, catchy names, right?
Yeah, they are catchy.
But what makes them different is all about the extra ingredients.
Interesting.
So think about making a cake.
Okay.
You've got a basic recipe,
Right.
but you can add different flavors or toppings, right?
Yes.
Similarly, the mantle rock is like the basic recipe for the MORBs.
Okay.
But the little extras that they pick up as they're forming give them their unique chemical signatures.
Oh, like little sprinkles.
Exactly.
Okay, so the names tell us something about what's in them.
Yeah, that's the idea.
Okay.
So are all these different MRBs found everywhere, or are they more common in one mantle domain versus the other?
Ooh, good question.
That's the cool part.
Okay.
You find all three types in both the African and Pacific domains, but there are consistent differences between them.
Oh, really?
For example, African MRBs generally have higher levels of certain isotopes like strontium-87 compared to their Pacific counterparts.
Ooh, so it's like they have slightly different spice levels.
Exactly.
Okay, so basically the mantle is way more complex than just a simple north-south divide.
You got it.
It's got this whole east-west thing going on,
That's right.
shaped by millions of years of plate tectonics and supercontinent formation.
And to analyze all this data,
Yeah.
figure out the differences between African and Pacific MRBs, the researchers actually used machine learning.
Hold up machine learning.
Yeah.
We're talking about cutting-edge tech being used to decipher these ancient rock formations.
It's pretty amazing.
That's so cool.
It's like having a superpowered detective at our disposal.
This is awesome.
I know, right?
We've learned that the mantle has distinct flavors.
Yeah.
It's got a wild history tied to Pangaea.
Uh-huh.
Scientists are using supercomputers to decode it all.
It's incredible, isn't it?
What's next? I'm on the edge of my seat.
Well, before we get too carried away,
Yeah.
let's delve into something even deeper, literally.
Okay.
Remember those giant blobs in the lower mantle?
Oh, yeah, the LSCPs,
The LLSVPs.
those mysterious giants.
Yeah, what's the deal with those?
I don't know, you tell me.
Well, this research suggests they're not just random blobs.
Huh?
They actually seem to be connected to the whole Pangaea story.
Ooh, this is getting good. Tell me more.
All right, so picture this.
Okay.
These LLSVPs, which stand for Large Low Shear Velocity Provinces, they're huge EE.
Okay.
They're like massive continents of very dense material just sitting at the bottom of the mantle.
Okay.
And what's cool is that both the African and Pacific mantle domains have them.
Okay, so we've got these giant blobs on both sides of our mantle, East Coast, West Coast divide.
Yeah.
What's the connection to Pangaea?
Well, the research suggests that these LLSVPs might have actually formed in connection with the supercontinent Pangaea. Remember how we talked about Pangaea concentrating more continental material into the African mantle domain?
Yeah, like Pangaea gave the African mantle its unique fingerprint.
Exactly. Well, it seems that the formation of Pangaea might have also played a role in the formation of these LLSVPs. It's a complex process, but essentially the way that the continents moved and the oceans closed during Pangaea's formation could influence where these dense blobs of material ended up.
So we're talking about events from hundreds of millions of years ago, still shaping the deepest parts of our planet today.
It really is.
That's crazy.
And it highlights just how dynamic and interconnected the Earth's systems are.
Yeah.
We often think of the mantle as this static layer, but it's anything but.
Right.
It's constantly evolving and changing in response to plate tectonics, supercontinent cycles, and even these mysterious LLSVPs.
You know, this research is making me see the Earth in a whole new light.
Yeah.
It's not just like a solid ball of rock. It's this incredibly complex and dynamic system.
It is.
This fascinating history.
I'm glad to hear that. It's one of the things I love most about geology. It's like piecing together this giant puzzle
Right.
where every rock, every formation, every chemical signature tells a story.
Okay, I have to ask, besides just being super cool, what are the implications of all of this?
Yeah.
Does it actually affect anything up here on the surface?
That's a great question.
Yeah.
And the answer is absolutely.
Oh.
Remember how we talked about different types of volcanic rocks?
Right.
Well, the composition of the mantle, including the presence of these LLSVPs, influences the types of magma that are produced, which in turn affects the types of volcanoes that we see on the surface.
So are we talking about different kinds of eruptions, different hazards? What does it actually mean for us up here?
Well, for example, some researchers believe that these LLSVPs could be linked to some of the most massive volcanic eruptions in Earth's history.
Really?
These eruptions are called Large Igneous Provinces, or LIPs.
LIPs?
Yeah, and they can have a significant impact on global climate and even trigger mass extinctions.
So these giant blobs deep down in the mantle could be responsible for some of the most catastrophic events in Earth's history.
It is.
It's a little unsettling.
It is, but it also highlights the importance of understanding these deep Earth processes.
Right.
The more we learn about the mantle, the better equipped we'll be to understand and potentially mitigate the risks associated with volcanic activity.
That makes sense. So like you can't really prepare for a hurricane unless you understand how they form.
Yeah,
right.
Exactly.
Same goes for volcanoes.
And just like with weather forecasting, the more data we have, the more sophisticated our models become,
Yeah.
and the better we can predict future events.
Okay, so we've got these giant LSVPs potentially triggering massive eruptions. Anything else we should be aware of?
Well, there's also the question of how these LLSVPs might influence the movement of tectonic plates. Some scientists believe that the presence of these dense blobs could actually influence how plates move and interact, which could have implications for things like earthquakes and mountain building.
Wow, so we're talking about like a ripple effect that goes from the deepest parts of the mantle all the way up to the Earth's surface.
It's incredible, isn't it? It's like this giant interconnected system
That's
where
amazing.
everything is influencing everything else. And we're really just beginning to scratch the surface of understanding how it all works.
You know, we've been talking a lot about the past and the present, but I'm curious about the future. If the mantle is so dynamic and constantly evolving, what does this research tell us about what might happen millions of years from now?
That's a fascinating question.
Yeah.
And it's one that scientists are actively exploring. Remember how we talked about the supercontinent cycle, how continents break apart and come back together over time?
Yeah, like a giant slow motion dance.
Exactly. Well, some scientists believe that the current configuration of the continents and these LLSVPs could actually be setting the stage for the formation of a new supercontinent millions of years in the future.
Whoa, really? So we might be living through the early stages of Pangaea 2.0.
It is,
Yeah.
and imagine the changes that that would bring to the Earth's surface.
Oh my gosh.
New mountain ranges would rise, new oceans would form, and the global climate would be drastically altered.
I'm getting chills just thinking about it.
It's pretty amazing.
It really puts things into perspective. Our human timescale is so short compared to these vast geological processes.
It really does.
Yeah.
And it highlights the importance of studying the Earth's deep past.
Right.
By understanding how the Earth has changed over millions of years, we can gain valuable insights into what might happen in the future.
You know, it's kind of humbling, isn't it?
Yeah.
To think about these forces that have been shaping our planet for billions of years, long before we were even a glimmer in the universe's eye.
It is.
Yeah.
And it makes you realize just how interconnected we are with this planet and its history.
Yeah.
We're not just living on Earth, we're a part of it.
I love that. Okay, so we've covered a lot of ground here. From ancient supercontinents to giant blobs deep in the mantle to the potential for a future Pangaea. Anything else we should touch on before we wrap up?
Yeah, there's one more really fascinating aspect of this research that we haven't talked about yet.
Okay.
It has to do with how these scientists figured all of this out.
Okay.
Remember how we talked about them using machine learning to analyze the data?
Oh yeah, that was super cool.
Right.
It was like they unleashed a supercomputer on these ancient rocks.
Exactly, and this is where it gets really interesting.
Okay.
You see, traditionally, geologists have used a lot of different techniques to analyze rocks and figure out where they came from.
Okay.
They look at things like mineral composition, chemical signatures, isotopic ratios.
Right, like that fingerprint analogy we talked about earlier.
Exactly.
Like,
But with the massive amounts of data that we're collecting from all over the world these days, it's becoming really difficult to analyze everything by hand.
that makes sense.
So that's where machine learning comes in.
So they're basically teaching computers to be geologists.
In a way, yes.
That's awesome.
They're training algorithms to recognize patterns in the data that might not be obvious to the human eye.
Okay.
And in this case, the machine learning algorithm was actually able to accurately distinguish between MORBs from the African and Pacific mantle domains, even when those differences were subtle.
Wow, so it's like the computer is this superpowered detective, sifting through mountains of data and finding these tiny little clues that reveal the secrets of the Earth's mantle.
That's a great way to put it, and it's opening up all these new avenues of research in geology because with machine learning, we can analyze data sets that were previously just too big or too complex to handle.
It's like we've got this new tool in the toolbox now
Exactly.
that lets us ask questions and explore ideas we couldn't even dream of before.
Exactly, and this is just the beginning. As this technology continues to advance, I think we're going to see even more groundbreaking discoveries in geology and all the other earth sciences.
It's really exciting to think about what the future holds.
It is.
So to wrap things up, what's the biggest takeaway that you hope our listeners walk away with today?
Well, I hope they come away with a sense of wonder and appreciation for how incredibly complex and dynamic our planet is.
Yeah.
The Earth isn't just a static ball of rock, it's this living, breathing system with processes happening deep beneath our feet that influence everything from the landscapes that we see to the air that we breathe.
You know, this research has really highlighted the importance of continuing to explore and understand these deep Earth processes. Because it's not just about rocks and minerals, it's about understanding our place in this vast, interconnected system.
I couldn't agree more. And who knows what incredible discoveries await us as we continue to delve deeper into these mysteries of the Earth's mantle.
Well said. A huge thank you to you for joining us today and sharing your expertise. This has been such an incredible journey into the heart of our planet.
My pleasure. It was great to be here.
And all of our listeners out there, thanks for tuning in. We hope you enjoyed this deep dive into mantle heterogeneity. Don't forget to check out the show notes for links to the research that we talked about today. Until next time, keep exploring.